Okay, the floor is yours.
Okay, thank you very much. Hello everyone, my name is Júnior Löff. I'm a PhD student at USI in Switzerland. And this is joint work done with Daniele, Bonetta, Matteo, Basso, and Walter Binder. And today we'll talk a bit about HeapBuffers. It's an efficient serialization library that actually can operate on data that is already stored in a binary format. So we will see what this is. So Google reports that 9.6% of all CPU cycles are spent just performing protobuf related operations, including data serialization and deserialization. And this isn't unique to Google. Every large-scale system will have similar overhead. So to understand where this number comes from, actually we need to have a bit of a background. So every programming language has its own way of organizing objects in memory, right? So on the left, I show how objects are commonly organized. You have the language implementation that can choose whether it wants to embed metadata in the header or exactly what metadata goes there. Objects can move, GC can move objects around. But overall, all this scheme is optimized for large and sparse object graphs. Now on the right, I show a binary layout where we have a different representation. Now we have a dense, small representation. More importantly, it's platform independent, okay? So we don't have the problem of pointers that are specific only for one virtual memory address. And overall, this is optimized for I/O and message passing. So why is it a problem? Well, every time we need to send a message, we need to convert from in-memory to binary, then we can push it to I/O, and on the other side, we need to reconstruct the object again. So this is actually an expensive operation, as I showed before. So it happens many times, billions of times per second across large-scale systems. And it's just an unavoidable cost we need to pay. It's often called a tax that we must pay just to transform, convert our data, but in fact, there is no useful computation happening here. So in this work, we challenge the need for this conversion. What if language VMs could bypass this close serialization by operating directly on a I/O-ready binary format? So this is the question we asked, and this is what we addressed with HeapBuffers. So before I show how our approach works, I want to quickly show some background, some related work on binary serialization in the JVM. So FlatBuffers is a prominent example for that, probably is the most popular one. It's a very efficient binary format. And in fact, our approach is binary compatible with FlatBuffers. However, there are two main problems that we identified. So the first one is performance, okay? So FlatBuffers is just a binary set of data. The VM cannot really see what is inside this binary data. It cannot see what objects are laid out. Because it cannot see it, it cannot optimize data access. As a consequence, accessing objects in such a way in FlatBuffers is more than 10 times lower than accessing standard Java objects. Secondly, less intuitive problem, but also a problem is limitations in the programming model. With FlatBuffers, developers, they must manually allocate objects in specific order, manually track offsets, and deal with immutable data. So overall, while FlatBuffers is a very efficient binary format, there is still a gap in terms of performance and programmability, and those are two things that we address with HeapBuffers. So as I mentioned, we are binary compatible with FlatBuffers, so we would inherit these problems, and actually we address this with our library. So what is HeapBuffers? So HeapBuffers design was guided by a simple vision. What if Java objects that are intended for data transfer, they could be already allocated in memory using a binary format? And this is exactly what we do. So let me highlight some of the key features. First, HeapBuffer objects, they are always allocated off heap directly using FlatBuffers binary format. What does it mean? It means that if we dump the memory of our runtime system, we have a valid FlatBuffers message that can be used in I/O. Likewise, if we receive a FlatBuffers message, we can also use the data right away without any deserialization. So we are able to bypass these operations. Secondly, we generate specialized code. I will talk a bit about this later, but actually we can generate code that is optimized for every message. And this means that we can trigger some compiler optimizations that where accessing HeapBuffer objects is almost as fast as accessing standard Java objects. Finally, we introduce a new programming model that can coexist with the existing Java programming model. And from the developer's point of view, it just feels like Java. We have automatic memory management, garbage collection support, and objects can be freely modified. So to understand how this works in practice, I will briefly introduce the workflow. We adopted the same workflow of flat buffers for compatibility reasons. And it all starts with a schema that describes the content of the message. So you have the objects, the relationships, and types. This is fed into the HeapBuffers code generator that will then generate specialized Java code specifically optimized for this message in particular. So the most important thing here is that since we know ahead of time what are the objects, what is their relationship, what is their types, we can actually generate very optimized code. So there are many things we generate in this code, but the two more important that I wanted to highlight are we generate a very efficient garbage collector. Okay, so every message has its own specific garbage collector that focusing on its own schema, and we also allow some tailored metadata that will be later used by GraalVM native image to optimize object access performance. Okay, so let's see the programming model. After we generate this Java file I just showed, we can include it in our application and start using HeapBuffer features. So before we see those, I want to introduce some concepts. HeapBuffer objects, they are allocated in a special memory region that is called transferable heap. Okay, so this is separated and isolated from the main Java heap. Here, all objects that are allocated will be HeapBuffer objects. They will have flat buffers layout, and they will be managed by their own GC. To access this transferable heap, we can use this method open, where simply accepts a lambda, and this lambda exposes the HP runtime to the user. So this is the only method where we actually have access. And what we want, our goal with this open, is to create a sort of dynamic scoping where it's clear for the user that he's actually modifying objects as are special objects, not regular Java objects. Okay? So let's see how we can create some objects using HP. So let's say we create some entities. They are directly allocated in the transferable heap. We can create an array. So far, E3 is a candidate to be garbage collected. And what we can see is that this looks just like regular Java objects, but under the hood, they are not. And actually, HeapBuffer objects, they have similar semantics as the upcoming Java value types from Project Valhalla. So we have more information about this in the paper. Let's continue our example. We can keep creating new objects. So this is the root of our message. We create a name and assign the array of entities. For the name, something special happens. This is a string. So for string is the only type in our system that actually it needs first to exist in a Java heap, and then we encode and copy it into the transferable heap. So there is an indirection here that later we will see in the experiments exactly what is the impact of this overhead. With our approach as well, we allow modifying objects. So let's say we didn't like the name. It's totally valid to set a new name. And finally, before we close this encoding, this scope, I want to show some broken code. So this is not valid. Okay, so this will not work. And the reason is that these two heaps, they are separate. So we don't allow HeapBuffer objects to reference Java objects, nor Java objects to reference HeapBuffer objects. So cross-references are not allowed. We only allow only two mechanisms can do it. One of them I already showed, which is the HP message in purple. So it always points to the root of the message. And then we have an additional mechanism, which is HP ref, that can be used to hold a reference to a HeapBuffer object. So this has weak reference semantics. It doesn't prevent the garbage collector from reclaiming the object. So before using it in the next time, you need to check whether the reference is still valid. Okay. Now we close the message. We call prepare. And what happens is that we trigger a GC cycle that will reclaim all unused objects, and it will compact existing objects into a dense representation. So from this point onwards, we have a ready-to-use flat buffers message. We can send it over the network, or we can continue using it in our application. We can call open as many times as needed, and we allow modifying and creating new objects. So then we implemented a prototype on GraalVM native image, and we conducted many experiments to evaluate whether this approach actually works. in this presentation, we'll focus only on end-to-end performance evaluation microservices, but in the paper, we have more experiments. So in this experiment, what we can see is that the outcome is highly positive. In 9 out of 12 applications, actually, we outperform the best serialization library in Java. And in the 3 cases, we achieve similar throughput, but still better latency. Now, zooming in the best case scenario, so what we are comparing here, measuring here actually is throughput and P95 latency. In the X scale, we have different message sizes. And we compare against Apache Fury, which is, so preceding experiment, we compared against many existing libraries in Java, and Apache Fury was by far the best, so it's our baseline. And we also compare against flat buffers since we are binary compatible with. For throughput, higher is better, latency lower is better. So overall, we can see that HeapBuffers outperforms in all message scaling sizes by many times, so 2.4 times for throughput and 4 times for latency. Finally, we also need to show the worst case performance. So this is the only case in all applications where we lose a bit to Fury. And the main reason is what I explained before. So this schema uses a lot of strings. So they add some memory pressure in our system because we need to allocate 2 times. And even so, we achieve actually a great performance. So we are comparable in most scales, but up to 8% lower throughput, and still we achieve better latency. So to conclude, I presented HeapBuffers, an efficient serialization library that can actually bypass serialization and deserialization, and this is done because objects, they are already allocated using an IO-ready binary format. So we demonstrated how we can use specialized code generation to optimize both performance, improve performance, and also improve flexibility in the programming model. And experiments have revealed that HeapBuffers can outperform existing serialization libraries in Java. So you can find more implementation details in the paper. I don't have time to cover all of them. And all our source codes are available in the artifact, including the modified Grau VM native image compiler. So thank you very much, and I'm happy to take your questions.
So we have time for a couple of questions. You will be the one this time.
Thanks, this is really interesting. The thing I've seen that's a bit like this, but I'm not sure it's that similar, is Cap and Proto, right? Because the idea of Cap and Proto is you have an in-memory representation that you can work with directly, so you do a computation on that, and you never have to re-encode to do your I/O. So is it a similar approach, would you say? Or?
Yeah, so actually, Cap and Proto is, I would put it on the same level as flat buffers. So right now we chose flat buffers, but actually we could have used Cap and Proto binary format for our approach. So our approach is built on top of this binary format.
Okay,
yeah.
Cool. I'll read the paper, thanks.
Yes. Sorry.
So maybe an answer to your title is debugging, right? Because the problem is debuggers rely on sort of a fixed layout in memory, and if you destroy that, then the debugger doesn't know anymore. Have you tried instrumenting a debugger with a sort of like a hook to allow it to read these serialized things to see whether you manage to get sort of the good experience with also the efficient format?
So actually we didn't try it, but it's a good idea. No, so far we didn't try to use a debugger in this. Thank you.
Hello. One question is that these heaps are garbage collected, or you fence the garbage collector from going inside and traverse these objects?
So, okay, so for this question first, thank you for asking. It's, we completely have a separate heap, so the regular GC doesn't touch our data.
And
we have our own garbage collector.
This heap is in memory, or is on a storage device?
No, it's on memory.
It's on memory.
Yeah. Of heap, but on memory, yes, on the main memory.
Okay, and continue my question is that, okay, you have this object there, so one opportunity is to avoid to fence the garbage collector from going and scan these, because I think they have the same lifetime. So when you perform heap deallocation, you can reclaim them together.
Yes.
Yeah.
Yeah. So actually, this was one of the ideas we had. Since these objects they have different semantics as regular Java objects, we can kind of specialize them. And for that, we implemented a very simple garbage collector. It's not as fancy as G1 or any of them, but it does a very good job. So we have measured the GC, the overhead of our GC, and it's really small.
Okay.
So we already took this into consideration.
Okay.
Yeah, later.
Thank you. Fine. Thank you so much.